Okay, good afternoon, everyone. I hope my voice is audible to you all and my slides are visible. I welcome you all to the eighth tutorial of the course Introductory Organic Chemistry 2, conducted by NPTEL, whose course instructors are Professor Hanina Chakrapani and Professor Niraja Dashaputri from ISER Pune. I am Deepika, your PMRF teaching assistant. I am doing my PhD in chemistry at IIT Bombay. And today on 14th October, we're going to take the last official tutorial of this course. So, till now, we have covered 7 tutorials on this course, and on this eighth tutorial, we are going to discuss a few advanced mechanisms of various rearrangement reactions. And uh, already we have discussed some similar mechanisms on the topics condensation chemistry. And so I hope this rearrangement chemistry will not be very difficult for you all. Okay. Okay. And I would advise you all to mute your audio so that it doesn't disturb the other students. So let us start today's tutorial. Okay. So let us start with this easier question, which is an unlikely product of the following hydrochlorination of an alkene. So you are given this alkene, internal alkene, and we are treating it with HCl. So you are asked which of these four given products will be formed in this reaction. So to know the major product of this reaction, and for hydrochlorination, you just have to understand the reaction as over this double bond, we are going to introduce H plus and Cl minus. Okay. But by mechanism, you have to identify which product you will get, because see, H plus and Cl minus you can introduce in either of this carbon of double bond. Okay. So the major product will be that one where the mechanism will involve the most stable intermediates throughout the reaction pathway. Okay. So let us analyze the reaction step by step. What will happen when we are going to add acid to this substrate? First of all, this double bond is going to attack the H plus present in the reaction medium. Okay, this HCl is going to be present as H plus and Cl minus. So this double bond is going to undergo nucleophilic attack on the H plus. And by that attack, you can introduce the H plus to either this carbon or this carbon. So which carbon we are going to choose? See, if H plus we are going to introduce at this carbon, we are going to get carbocation at this carbon. Okay. And similarly, if we add the H plus here, we are going to get the carbocation at this carbon. Okay. So you have to check which carbocation is more stable, which will be formed in this reaction. Okay. So this is the description which is given for this reaction. See what will happen. First of all, and we are asked which is unlikely product. Okay, three of these is possible for the reaction and one of these is not possible. Three of this is, how is it possible? Because the neighboring carbon of this double bond is containing alkyl groups. Okay, so this intermediate carbocation which is going to form this can undergo rearrangement as well, which can undergo 1 to alkyl shift as well. Okay, So by that, two other products are also possible. So one of these is unlikely product for this hydrochlorination. So suppose we are introducing the H plus at this carbon. In that case, we are going to get the carbocation here. Okay? And that carbocation is going to be attacked by Cl minus, and you will get A as the product. Okay? So A is very likely, A is possible as the product for this hydrochlorination. And then in another possibility, what can happen? H plus can come here. Okay, if H plus comes here after the attack, carbocation will be generated at this carbon. Okay, and this second carbocation will be now attacked by Cl minus in the medium, and you will get B as the product. Okay, you can get B as the product. And then another possibility is present out of these four options, right? What will happen in that case? Suppose the carbocation is getting generated at this carbon, okay, and the neighboring carbon is containing two alkyl change which can undergo 1 alkyl bond, okay. And if that alkyl shift happens, sorry, not alkyl, see, if we talk about migratory aptitude, which is already covered by Professor Harina Chakrapani sir, between hydride, alkyl and aryl, if we look at the migratory aptitude, which we are also going to discuss in this tutorial, hydrides will shift readily. Okay? In that case, if the carbocation is generated at this carbon, this hydride can undergo shift to this carbon. And in that case, we are going to get the third possible carbocation intermediate at this terminal carbon. Okay, and in that case, after the hydride shift, we are going to get the carbocation center here, which will be trapped by the incoming Cl minus, and you will get C as the major product in that case. Okay, first we generated carbocation here, then we shifted hydride here because hydride has the most migratory aptitude. So after that, whatever carbocation we are going to generate at this carbon, that one will be trapped by Cl minus, and you will get C as the product. So like this, we have found that A, B and C are possible to be formed in this hydrochlorination of alkene reaction. But D cannot be formed by any of these cases. Okay, we are not going to get carbocation center at this terminal carbon by any case because we are already getting secondary carbocation centers in the other three possibilities. So no possible way of forming the primary carbocation here is seen in this reaction. Okay, so we will not get D as the product of this reaction. So if you are asked that which is unlikely product, like which product of these will not be formed in any case of this hydrochlorination, then you have to answer that option D is the correct answer. And you can note down the brief description of this answer as well. But if you understand that how we are going to form the stable carbocations, then you will know that yes, the other three possibilities are there where we are going to get secondary carbocations, but this primary carbocation case will not be observed for this reaction. So let us move to the next question. This is now coming from the main topic of this tutorial, which is rearrangement reaction. Okay, which of the cations A to D is the least likely to be an intermediate in the following rearrangement reaction? So, when it comes to rearrangement reaction topic, what are the first rearrangement reactions that we study? Those starts with pinacol pinacolone rearrangement. Okay, so this is a question from that same topic. So you are given this diol, which is commonly known as pinacol, and we are treating it with acidic solution. And as a result of this reaction, we are getting pinacolone, which is this ketone, as the final product of this rearrangement reaction. And throughout this reaction mechanism, reaction pathway, we are going to involve a few reactive intermediates in the reaction, isn't it? Carbocations, carbon ions, various reactive intermediates we are going to involve in this reaction. So you have to identify out of A to D which is that reactive intermediate that is not going to be formed. So let us revise the mechanism of pinacolone rearrangement. Okay, so this is the substrate that is given to you, and when we add acidic solution to this substrate, what happens? One of the hydroxyl group will get protonated. Okay, the lone pair of electron of one of the hydroxyl group will be donated to the proton present in the acidic medium, and as a result, we are going to get this oxonium. Okay, now this oxonium intermediate is containing a very good leaving group, which is a water molecule. Okay, if this leaving group is knocked out of this substrate, we are going to get a neutral water molecule, and this is why this oxonium is containing this OH2 positive as a very good leaving group. Okay, so in the subsequent step, this good leaving group leaves, and it leaves behind this carbocation center. Okay, this is a tertiary carbocation which is stable. And what happens, this after the formation of this, along with the formation of this carbocation, we are knocking out this neutral water molecule in the second step. And then in the next step, what happens? We get methyl group shifting, which is commonly observed in rearrangement reaction mechanisms. So here also, this methyl group from the neighboring carbon leaves, and it shifts to the carbocation center. Now you get the second carbocation, which will be neutralized by electron push from the second hydroxyl group. Okay, this lone pair of electron which is present on the oxygen will be pushed towards the new carbocation formed, and you, as a result, will get the second oxonium ion. What will be that second oxonium? You will have carbon oxygen double bond here, and this oxygen will first contain this proton, which will be deprotonated from the medium, and you get this pinacolone as the final product. So you have already come across this similar mechanism from the video lectures. So these are the four steps that pinacol pinacolone rearrangement reaction involves. And throughout the mechanism, we observe a few reactive intermediates, which are this oxonium and then these carbocation centers we observe, and here also another oxonium we observed. So let us come back to the question and look at the intermediates given. Did we come across option A in the reaction? Yes, in the first step itself, this intermediate formed. Then, did we come across option B, where both the hydroxyl groups are getting protonated and containing two good leaving groups? No, we did not come across option B. We only protonated one hydroxyl group, and immediately we knocked out that water molecule. Okay, two oxonium in a single substrate is not possible. That will lead to a very high destabilization of the system. Okay, even after forming one positive center at this oxonium, we immediately knock out this water molecule. Okay, so option B we did not come across. Okay, and if we talk about option C, yes, we did come across option C, how after oxonium formation, when we knocked out the good leaving group, we obtained the formation of option C. Okay, and option D also, if you remember, at the end, when we neutralized the second carbocation, like here, na, like here, when we neutralize the second carbocation formed, the electron push from the oxygen led to the formation of carbon oxygen double bond, and we got the second oxonium possible in the reaction mechanism. So now we have figured out which is that intermediate that we did not come across in this pinacol pinacolone rearrangement reaction. It is option B. Okay, all other cations we came across, A, C, and D, we saw in the reaction medium. So you have to choose option B as the correct answer in this reaction. So I hope with this question you are again we have you have again been able to revise the mechanism of pinacol pinacolone, and you have also understood the kind of intermediates that we come across in this reaction. So after this, let us move to the next question. So yeah, this is the answer for this question. And in the next question, which carbonyl compound is the main product of the following reaction of a diol? So again, this is a question from the topic pinacol pinacolone. But in this question, concept of migratory aptitude will be used. Okay, because the substrate, if we see, this is not a symmetric substrate. Okay, both the central carbon atoms, which are containing the diol, these two are not symmetric. They are having different substituents on them. So the concept of migratory aptitude and concept of formation of stable carbocation will come in this question. So you have two hydroxyl groups here. Now you have to identify which of these hydroxyl will get protonated so that we get the formation of the most stable carbocation. Suppose this hydroxyl group is leaving. We are going to get a tertiary carbocation here, which is linked to two methyl groups and one alkyl chain. This long alkyl chain will be there. Okay, that is the first carbocation possible. And if we talk about the second possibility, if the second hydroxyl group leaves, then also we are going to get a tertiary carbocation where the carbon atom is linked to this ethyl group, this phenyl group, and this long alkyl chain you can imagine. So out of these two possible carbocation formed, which is more stable? Definitely the one with the phenyl group linked to it will be more stable. Why is it so? Because electronic conjugation from the phenyl ring or and also electronic donation from this more electron rich ethyl group will lead to more stability of this carbon center. So in the first step you have to protonate this hydroxyl group. Okay, this hydroxyl group you have to protonate, which will be knocked out as neutral water molecule, and you will get a carbocation at this carbon center which is linked to phenyl and ethyl. Okay, this carbon will form the carbocation in the second step. So after the formation of of the first carbocation, what happens in the pinacol pinacolone? The neighboring alkyl shift take place. Okay, so one of the methyls from here will shift to this carbon atom, and you will get the second carbocation here. and then at last you will get carbon oxygen double bond formation here. So you have to identify the product where you are going to get the product with a keto functionality linked to a methyl, and and the alpha carbon is going to be linked to phenyl, ethyl, and the migrated methyl. Okay, so after writing the mechanism step by step, you have to identify which of these are containing such functionality. Okay, so while solving these questions, you may require this migratory aptitude page. You can take a screenshot or note down. These have also been discussed in the video lecture. Okay, so we will not spend much time on this page. And like I said, in the product, you will have a methyl link to the keto group, and the alpha carbon will contain phenyl, ethyl, and the migrated methyl. Okay, so in this particular question, the most important thing that you have to identify is which is the most stable carbocation that is going to be formed in the reaction. Okay, because we had two possibilities of formation of carbocation, but we chose that carbocation which was linked to phenyl and ethyl, and both of these are pushing their electron density towards the positively charged carbocation, thereby making it more stable carbocation as compared to the other one, which is linked to two methyl groups. Okay, so this is why you will get option D as the correct product for this pinacol pinacolone rearrangement. So after this, let us move to the next question. This is another example of pinacol pinacolone rearrangement, but in this particular question, you have to now look at the presence of a good leaving group already. Okay, OTS is a very good leaving group. This oxygen, which was initially hydroxyl in the other questions, now this oxygen is linked to a tosyl group. What is a tosyl group? It is, imagine toluene, methyl substituted phenyl, and that phenyl is linked to SO2. That is the tosyl group. Okay, so this oxygen is now linked to tosyl group, and this OTS is known to be one of the best leaving groups in organic chemistry. So you already have a good leaving group in this substrate for this reaction. Okay, so let us now see that under the pinacol pinacolone rearrangement reaction conditions, what type of mechanism will this particular substrate follow? So what happens, since we have a good leaving group already, in the first step of this pinacol pinacolone rearrangement, protonation of this oxygen will be preferably taking place. Okay, earlier we were protonating the hydroxyl groups because we were getting water as a good leaving group. Okay, but in this case, since OTS is already present here, this group will now be protonated first, and as a result, you have to form the intermediate at this carbon center. Ideally, if it was hydroxyl, we would have preferred to form the carbocation here because we were getting a tertiary carbocation which is more stable. But now we cannot choose the one where we get the more stable carbocation. Rather, the first step will be dictated by this leaving group only. Okay, because after knocking out this leaving group, only the carbocation will form. Okay, so at first this OTS will be protonated, and this will be
leaving out as uh, the TSOH acid, and in the subsequent step you will get carbocation center generated here. And what happened in the third step of pinacol pinacolone? 1 to alkyl shift happens. So here you have alkyl groups CH3 CH3, so any of these CH3 will shift to this carbocation center, and subsequently in the fourth step and the last step you will get a keto functionality at this alpha carbon, isn't it? So if you look at the products, which product is matching the mechanism discussed? See, we have a product where this carbon is attached to a methyl, a hydrogen, and the to ethyl hydrogen and the methyl, which will be migrated, and then the other carbon is going to be attached to a methyl which is not migrated and a keto functionality. So it is matching with the option C. Okay, so it is matching with the option C. Thus, this particular reaction is going to follow a little different mechanism than the other pinacol pinacolone rearrangements which we have discussed. The good leaving group present in the substrate will dictate the mechanism that it is going to follow. Okay, I hope that was clear.
Excuse me, madam.
Yes,
In the previous example,
yes,
there is a pinnacle rearrangement.
yes.
Protonation is done, but the reaction medium is aqueous, not acidic. How can we protonate the substrate?
Okay, it is written water, but yes, water from water medium only it will abstract proton, because you will have H plus and OH minus in the medium, right? And this OTS is already so good leaving group that you do not necessarily require acidic medium. From water medium only it will take up proton. Okay, even very mild acidic medium is required for the protonation of OTS, so that it just can leave as TSOH. Okay,
Okay,
you
okay.
already have H plus and OH minus in the water medium, so you do not need a stronger acidic medium for this reaction.
And here it is OTS already is a ionic part.
Uh, it in the substrate it is present in the neutral form. You can consider it CO, which is linked to sulfur, and that sulfur is containing two oxygen on the both side, and that sulfur is also containing toluene substituent. So it is actually present in the neutral form, but when you subject it to water, this O will form oxonium, and then as a leaving group you will get a acid which is TSOH. Okay, paratoluene sulfonic acid will be the leaving substance here.
Yes, madam. Yes.
Yes. So from the water only you can protonate the this OTS group, and you will get that oxonium in the first step. So like that, you saw that OTS present in the substrate is dictating the mechanism to follow a little bit different pathway, and that is why this reaction is termed as semi-pinacol rearrangement. So let us move to the next question now. Which is the main final product of the following diazotization of an amine? So, although not much of this topic has been covered in the video lecture, but this is also another type of rearrangement reaction where you have this amine and we are subjecting it to diazotization condition. Okay, so which of these products will be formed in this reaction? So first what happens, this amine will undergo this well known condition of diazotization. So this amine will first get converted into diazo group, that is N2 group will be linked to this carbon in the first step of this reaction, and on the subsequent step the rearrangement will take place. Let us look at the mechanism how this rearrangement is going to take place. So suppose we have this exemplary substrate which is containing an amine and also beta hydroxy group in the substrate. Okay, so we subject it to the diazotization condition, and from the diazotization condition we have this NO cation formed by the reaction of NaNO2 and HCl in presence of water. Okay, and the amine will undergo reaction with this NO positive cation, and you will get two other reactive intermediates in this course of the reaction. Okay, but this is not much of our importance because you have already studied the diazotization reaction. We just have to look at the last intermediate which is going to form. This one will get converted to the diazo group, where in place of this amine you will get a substrate where you will have N2 linked to this carbon. Okay, and that particular intermediate will knock out the neutral nitrogen molecule and you will get a carbocation at this position. Okay, and also you have a beta hydroxyl group. So after the formation of this carbocation in this reaction, the hydroxyl oxygen lone pair will be pushed towards this beta carbon, and 1 to alkyl shift will take place to this carbon. Okay, the last step will be exactly similar to the third and fourth step of pinacol pinacolone rearrangement that we discussed, okay, for the second question. So here also, like I said, the oxygen lone pair will be pushed and one of the methyl group will be shifted to the first carbocation that formed, and in the final step you will get this ketone as the major product. So let us look at our substrate, what is there present. At first the diazo formation will take place in this nitrogen, and that after leaving, after knocking out the neutral nitrogen molecule, you will get a carbocation at this carbon. Okay, after that what will happen, what we saw, the beta hydroxy oxygen will push the electron pairs towards the beta carbon, and since it is a symmetric substrate, you do not have to worry about the migratory aptitude of these two chains, okay, because both are same only. So one of these alkyl chain will migrate to this alpha carbon, and you will see ring expansion in this case. Okay, so since it is a cyclic substrate, you will observe ring expansion, and this alkyl group, if we are shifting, you will now get another ring which will have 1, 2, 3, 4, 5, 6. The ring will now have 6 members in the ring, and you will have a keto group, and in the previous alpha carbon you will have a methyl substituent. So out of these four options, option D is matching with the product that we are predicting. Okay, you can note down this particular slide, which is showing how the reaction is going from the initial amine, which is beta hydroxyamine, to the ketone functional group. And thus we got the ring expansion in this substrate, and this is the brief description of the explanation of the reaction. Okay, so thus after the diazotization we observed a rearrangement in the substrate, and we got a ring expanded product. So let us move to the next question. Which is the main product of the following reaction of an amide? So you are given an amide here, and we are treating it with bromine in presence of sodium hydroxide in water medium. Okay, water as a solvent we are using, and you are given four possible products, two of which are amine. And in option A, yeah, if you talk about the change, you just have to change this CO into CH2 for option A. And for option B, one carbon is less than the substrate. In option C, the amide functionality is changing into a carboxyl group. And then in option D, you can see the position of CO double bond functionality of the amide is changing. Okay, it is changing in the option D. So let us identify what kind of mechanism this substrate is following. This is the well known Hoffman rearrangement. When it comes to the reactions where we get chain length decrease, in that those cases Hoffman rearrangement reaction is very well practiced. Okay, whenever you want to convert a substrate to another substrate with one carbon less in the product, in those reaction strategies Hoffman rearrangement is very highly preferred. Okay, that means whatever will be the carbon number in the substrate, in product you will get a less number of carbon. Okay, so let us see how this reaction proceeds. First of all, we are treating the amide with bromine. So amide, NH2 of the amide is containing lone pair of electrons. So it will undergo nucleophilic attack on the bromine, and one Br minus will be knocked out in the reaction. So you will get this N-bromoamide as the first intermediate product of this reaction. Okay. So after the formation of N-bromoamide, in the second step, migration of alkyl will take place, where you get isocyanate as the reactive intermediate. So how is it happening? You have this N-bromoamide, and this nitrogen bromine bond is very weak. Okay, so what happens, the alkyl from this carbonyl group will migrate to this nitrogen atom, and this bromide will be knocked out. So as a result, you will have this isocyanate as the major product. Okay, and in the course of this second step, water molecule will be the side product. Then after the formation of this isocyanate, what happens, it can react with the water molecule in the medium. So this water will get added to this isocyanate to give you carbamic acid. Okay, In this isocyanate, this carbon atom is highly electrophilic, okay, because its electron pairs are getting pulled both the sides by these two electronegative atoms. Okay, so this water molecule lone pair of electron will be donated to the electrophilic carbon, and you will get this carbamic acid formation as the third intermediate product in the reaction. And then what happens in the last step? This carbamic acid will now be degraded by the water molecule. Okay, it first undergoes deprotonation by the water molecule, and in the subsequent step it leaves, it undergoes decarboxylation to give you this anion as an intermediate, which will now get deprotonated, which will now undergo protonation to give you amine as the final product. So this decarboxylation step is one of the most important steps of Hoffman rearrangement, because this is explaining to you why we get a carbon number less in the product, because that particular carbon is leaving as carbon dioxide in the reaction mechanism. So, thus, this Hoffman rearrangement reaction is following this pathway where you get this isocyanate as a very important reaction intermediate, which converts into carbamic acid, and lastly you get amine as the final product due to decarboxylation. So let us now go back to the reaction where we were given an amide and we treated it with bromine sodium hydroxide in water. So like we saw from the Hoffman rearrangement reaction, we observed the formation of amine with one carbon less in the product. So, out of A and B, see, since amine is the final product, either A or B will be the main product. Okay. So, out of A and B now, we have to choose B as the final product. Okay. Where we have one carbon less, because this carbonyl was being knocked out as carbon dioxide in the mechanism. So you have to choose B as the final product. So in the video lecture, we have come across a lot of rearrangement reactions where we involved this isocyanate as the intermediate. Okay. So many such mechanisms we will discuss in this tutorial in the next questions. Okay. So remember this isocyanate intermediate. After the formation of this isocyanate in all these various rearrangement reactions, they will react with either water or alcohol or amine, and they will lead to the formation of various different products in the reaction. So now let us move to the next question. Which of the following equations shows an unlikely main product? So you are given four reactions in this question, okay? First one, you have this amide, and this amide is treated with bromine sodium hydroxide water, and we are getting an amine and carbon dioxide as the uh, side product. So we have just now discussed this reaction. This is the well known Hoffman rearrangement. So for if we talk about the products, are we getting an amine with one carbon less? Yes, definitely. And that carbon is leaving as carbon dioxide? Yes. So you can quickly choose option A as a correct main product, and you can quickly eliminate option A to be a correct answer for this question, because we are asked which is unlikely main product. Okay, this is definitely its likely main product, so we can eliminate option A. After that, option B is given, where we have acid chloride now, and this acid chloride is now being treated with diazomethane in water, and we are getting this acid as the main product. So which reaction is this particular option involving? Let us look at its possible mechanism. It is following the Curtius rearrangement pathway, where at first you get acyl azide by the reaction of acid chloride, and if you have diazomethane as well, in that case also it will follow a similar pathway, where you have to eliminate a nitrogen molecule and you get isocyanate as the intermediate of the reaction. Okay, so if you have, suppose, KN3 or sodium azide, potassium azide or sodium azide, if you have in the reaction medium, this will be the reaction pathway that the substrate will follow. At first, you will have acyl azide, and in the next step, you will have nitrogen molecule elimination, and you may get nitrene as the reactive intermediate, which will quickly get rearranged. Like this alkyl will shift to the nitrogen, and you will get isocyanate as the preferable reactive intermediate in this reaction. Okay, and this in this particular slide it is also showing how this Cr sigma bond is being broken, and that Cr sigma is donating its electron pairs to the p orbital of nitrogen. Okay, and thereby forming a new sigma bond, and you get isocyanate as the main intermediate for this reaction. And like I said, in these rearrangement reactions, the isocyanate may react with alcohol or water or amine in the subsequent steps, and you get various different important products as the final product. And also, these products may undergo decarboxylation to give you finally amine as the main product. But you must remember that it is only the Hoffman rearrangement case where we got one carbon less, but in this Curtius rearrangement, the decarboxylation step does not necessarily happen, and it in most cases is it stops in these possible product stages. Okay, for Curtius rearrangement reaction, this decarboxylation step is not very common. Okay, so let us go back to the reaction. If we look at option B and D, these two are following a similar mechanism for the reaction. And for option B, you can see that after the formation of isocyanate, when it reacted with water, it gave this carbamic acid. Okay, so yes, in option B also, you are getting this acid as the product, but you must know that in this reaction you will not get isocyanate as major product, you will get a carbene as major product. Okay, but the product shown in this reaction is correctly shown, and you will get this acid as the major product for this reaction. And for option D as well, it is clearly following the straightforward Curtius reaction mechanism, and it is, since it is involving decarboxylation, you can expect the formation of this amine as the major product. So it is directly following this particular pathway. So option D also is showing the correct product for the reaction. For option C, you have to remember the mechanism of Baeyer-Villiger oxidation. Okay, so what was the mechanism of Baeyer-Villiger oxidation? We have a ketone first, which is reacted with per acid. Although most commonly people use MCPBA, metachloroperbenzoic acid, but any per acid whenever in the reaction condition is given, you have to identify that reaction that yes, this may follow Baeyer-Villiger oxidation. So a ketone is treated with per acid with this peroxide linkage. Here you can see, and this oxygen of this carbonyl will abstract the proton from this per acid, leading to the formation of this protonated ketone and also the anion after the taking up of proton, which is called as per carboxylate. Okay, so in the next step, the protonated ketone will undergo reaction with this per carboxylate to form this kind of intermediate where you get a carbon oxygen bond formation. Okay, but this intermediate which is formed is highly reactive. Okay, this is not stable due to this oxygen peroxy linkage. It is highly unstable, so immediately it will undergo rearrangement, and the arrow pushing, you can see it starts from this protonated ketone hydroxyl, which is newly formed, and this oxygen will push its electron pairs towards the ketone carbon, and this peroxy linkage, which is very reactive, will undergo cleavage. Okay, this OO will cleave, and you will get this protonated ester as the major product, and also carboxylate will leave. See, this fragment is leaving as carboxylate, and this first fragment towards to till this oxygen is going to give you the protonated ester. Now, simply the protonated ester will undergo deprotonation, and you will get this ester as the main product of Baeyer-Villiger oxidation. So basically, the ketone is getting oxidized to ester. This is why it is called Baeyer-Villiger oxidation. And you must know that if you see step 3, we are shifting an alkyl to the oxygen of peroxy linkage. And in this step, if you have R1 and R2 different, you have to choose alkyl chain or aryl chain according to the migratory aptitude. Okay, that alkyl shift will always follow the migratory aptitude order. So suppose you had phenyl and methyl here, you have to uh, you have to shift the phenyl preferentially to the peroxy oxygen. Okay, so if we look at the option given to us, this condition is involving a per acid. Okay, so trifluoroacetic acid we are using, and in this not acidic, per acid. So in this per acidic condition, we have this ketone, and in the reaction medium we saw that the alkyl shift to the peroxy oxygen was following migratory aptitude. So out of these two alkyl groups, if we see which one will be preferred for alkyl shift, definitely this tertiary butyl one, isn't it? This tertiary butyl one, which is tertiary, will be shifted more preferentially over this secondary one, primary one. Okay, so according to the migratory aptitude, You must get the oxygen coming from the peroxy linkage linked to this tertiary carbon. But in the product, as you see, the primary alkyl group is linked to the oxygen which is coming from the peroxy linkage, which was here. Okay, we see that in this option primary alkyl group is shifting, not the tertiary one, which is violating the rules of well known migratory aptitude. Okay, so you have to say that option C is not showing the correct main product. Okay, so you have to choose option C as the correct option when it comes to the option which is showing the most unlikely product in the reaction. Like it is written here, tertiary butyl has a higher migratory aptitude than ethyl to give the alternative ester as the main product. Which is the alternative ester? That is, O will come here and this ethyl will be linked to the carbonyl of ester. That should be the correct main product of this reaction. So you have to choose option C as the correct option. Let us move to the next question. Which lactam will be the main product of the following rearrangement of an oxime when cis trans isomerization of the oxime is retarded? Okay, so by looking at the oxime, you may have already predicted which rearrangement reaction are we going to talk about in this reaction. It is the well-known Bachmann rearrangement. Okay, so you have already studied Bachmann rearrangement where the oxime first reacts with acid. Most commonly, the acid can be sulfuric acid, PCl5, etc. etc. So, this acid is, if we talk about the role of this acid, it is just converting this OH of the oxime to a better living group. Okay, so it gets converted into a better living group first, and after the formation of this oxonium, alkyl shift happens, and in Bachmann rearrangement, the bond which is anti to the oxime OH gets shifted. Okay, since this oxime CN double bond is in E form, consider it in E fashion, and always shift the alkyl bond which is anti to the OH. Okay, this bond is anti to this OH, so you have to shift this alkyl to the nitrogen. Okay, and as a result of this shift, the good leaving group water molecule will be knocked out, and you get this particular carbocation as the reactive intermediate in this reaction. So now you have the water molecule in the medium. It will now again attack at this carbocation positive center, and you will see that this carbon nitrogen double bond is hydroxylated in the subsequent step. Okay, and now you can say that tautomerism happens in this intermediate product, and you get this amide as the final product, which involved ring expansion in the reaction medium. Okay, so this is the simple mechanism which Bachmann rearrangement follows. Okay, you just have to remember a few points in the mechanism, that always you have to shift the anti alkyl bond which is anti to the oxime hydroxyl group. Okay, and in the towards the last step, tautomerism of this hydroxylated carbocation happens and you get this amide which is ring expanded as the final product. So we were also given a Beckmann rearrangement here, and the acid which is PCl5 will first convert the hydroxyl group of oxime into a very good leaving group. And how will that group leave? The bond anti to the oxime hydroxyl will shift to the nitrogen atom. So out of all the products given here, you have to choose the one where this alkyl group is shifting to nitrogen. Okay, which product is relating to the mechanism? It is definitely this option A1. Okay, option A is giving us the proper shift of alkyl chain to give us this lactam ring. Okay, so I hope the mechanism of Beckmann rearrangement was clear to you, and the anti-alkyl shift will give you option A as the final product. Then we have a bicyclic diol in the next question, and we have already discussed this topic extensively. It is coming from the topic pinacol pinacolone rearrangement. But since you have cyclic substituents this time, so do not get scared. Just go step by step in the mechanism, and you will get ring expansion of one particular ring for this example. Okay, so what happens first? We have already discussed the mechanism. This one, since it is symmetric, any of the hydroxyl group you can protonate first. Okay, and it will immediately undergo dehydration. Like the good leaving group, which is water molecule, will leave, and you will get a tertiary carbocation here. Okay, and I hope you remember the next step of pinacol pinacolone. What happens in the next step? In the next step, one of the alkyl groups from the alpha carbon will shift. Okay, these two are alkyl groups, so any of the alkyl groups will shift here, and also electron push from this oxygen will happen, and you will get a keto functionality here. So basically we are getting a product where this ring will get expanded, that is you will get a 5-membered ring, and that 5-membered ring will be containing a keto functionality. Okay, so I hope this question is now being very easy for you, because we have already discussed 3-4 questions on pinacol pinacolone. So if you get go step by step, option A you will get as the final product. Like I said, one ring of both the rings will get expanded, and that expanded ring is containing keto functionality due to electron pair push from the second hydroxyl group. Okay, so thus you will get option A as the correct answer for this question. So let us move to the next question now. The following diol 1 and bromo alcohol 2 could possibly give carbonyl compounds A and or B by the indicated reaction. Which are the expected results? So here you are given two reactions. Okay, for reaction number 1, you have this diol as substrate, and we are treating it with acid, aqueous acid solution, and it can give either A and B or A or B. One of these will form, or maybe both will form. That is reaction number 1. And for the second reaction, we have this bromo alcohol. Okay, and we are treating bromo alcohol with silver nitrate, in aqueous medium, and this one is also going to give either A and B or A or B. Any one of these can form or both of these can form. Okay, so in the question you have to choose, is both 1 and 2 giving you mainly A, or both 1 and 2 give mainly B, or diol 1 gives A but 2 gives B, or diol 1 gives B or 2 and 2 gives A. So it is, you may find it a little tricky at the first glance of this question, but don't worry, don't get scared. This question is also a very easy question. You just have to go one step by step for both the reactions. Okay, so let us analyze the reaction, what kind of mechanism these two reactions are following. So if we talk about reaction number 1 of this diol, it looks like it is involving the pinacol pinacolone. Okay, so what will happen first? Let us let us protonate any of these hydroxyls. So which one you will protonate? The one where you are going to get a more stable carbocation. Okay, so if we protonate this one, you are going to get a secondary carbocation here. But if we are going to get protonate this one, we will get a tertiary carbocation here, which is definitely more stable, isn't it? So we will protonate the hydroxyl group, where we will get the tertiary carbocation. So yes, after protonation of this hydroxyl, the good leaving group water molecule will leave, and after the formation of this carbocation, you have to shift, you have to involve 1 2 shift. Okay, and now you have one hydride here and methyl a methyl here. Okay, so which one we are going to migrate, hydride or methyl? According to the migratory aptitude, hydrides have the highest affinity for undergoing 1 2 shift. Okay, so since we have a hydride here, we are going to shift the hydride from here to here, and also this electron pair are going to be pushed, and as a result you will get this ketone as the final product. Okay, so yes, if reaction 1 is undergoing pinacol pinacolone rearrangement, we are going to get option A, I mean product A, as the major product. So let us keep that in mind, and then let us analyze the second reaction. So always remember, silver has a very high affinity to react with halogens. Okay, and most commonly bromine. Silver has a very high affinity for bromine, and it can easily form silver bromide salts. So whenever you have this bromo alcohol and you are treating it with silver nitrate, the silver ion of silver nitrate will extract the bromide from here. Okay, and after the extraction of bromide, this carbon bromine bond is breaking, isn't it? And you will get a carbocation at this center. Okay, so after the formation of this carbocation at this center, the rest of this mechanism you are going to get similar to the um, pinacol pinacolone. Okay, simply this bromine will leave first in this reaction, and after getting this secondary carbocation, one of this methyl group from the alpha position is going to be shifted to this carbocation, and also electron push will give you a keto functionality here. So you are going to get again option A, I mean product A, as the main product of this reaction. It's just written in a reversed way. Okay, it is just written in a reversed way, but ultimately
reaction 2 is also going to give you A as the product. I hope you understood the mechanism. Silver is going to extract the bromide, and you are going to get a carbocation here, which is going to undergo 1 2 shift from here, and you will get a keto functionality here, which is basically giving you the product A. Okay, so thus both 1 and 2 are going to give you the same product, which is product A. And this is the brief description for the answer. Diol 1 gives mainly the tertiary carbonium ion, which undergoes 1 2 hydride shift leading to A. And also, in case of the reaction 2, the bromide group leaves first, and then it undergoes 1 2 methyl shift to give you the same oxonium ion as the oxonium formed in option 1. So in both the cases you are going to get product A, but definitely both the reactions are not following the exact same pathway. Okay, only the product formed are same. So I hope the reaction mechanisms for both the reactions were clear to you. Then let us move to this interesting question. Which is an unlikely product in ethanolysis of the following methoxytosylate? So you have this methoxytosylate given, and we are treating it with ethanol. Okay, so you are said that out of these four products, three products are possible to form in the reaction. Okay, but one of these will not form in any situation. Okay, I hope you understand. Three of these products are going to form in the reaction, but one product will not form. So you have to just identify which is that product that is not going to form in the reaction at any cost. Let us look at the reactive intermediate that is going to form in the reaction. So what happens first? Like the previously discussed question, here you have this OTS good leaving group. Okay, of course, methoxy is also found to be a good leaving group, but for that you need a slightly more acidic condition as compared to OTS. Okay, for if you want to knock out OTS as leaving group, you only need a very less amount of protonating source, not necessarily acid. Okay, so if we compare OME versus OTS, OTS is very good leaving group, better leaving group, and it needs a very less amount of protonating source. So, in the first step itself, in presence of ethanol, this OTS group is going to be protonated, and neighboring group participation from this oxygen will will increase the rate of this leaving group knocking out, and you can imagine a intermediate of this kind. Okay, this OME lone pair can take part as a neighboring group participation, and that will elevate the rate of OTS knocking out, and you will get a intermediate of this type. So now what are these arrows showing? These arrows are showing the possible points where ethoxy ion from ethanol, see ethanol is containing H plus and ethoxide anion. Okay, so in the subsequent step of this reaction, ethoxy anion can come and attack at any of these three possible positions, because you have a oxonium due to the neighboring group participation of OME, and this oxonium will want to get opened up. so that it can get neutralized. And that neutralization will happen with the help of ethoxide. But you just have to identify the positions where ethoxide can attack. See, if ethoxide attacks at this first possibility, you will have a product which is option C. Okay, you can write down the product. What will happen if the ethoxy will attack at this carbon, and that product will be option C. So now we know that option C is going to form as a product of this reaction, and you can straight away eliminate option C from this question because you have to choose which product is not going to form. So option C we are eliminating. Now let us look at this arrow. What will happen if ethoxide is going to come from this way and going to attack at this carbon? In that case, you are going to get a product which is option A. You can write down the product. Ethoxide will attack here and this carbon oxygen bond will break, and you will get a long chain which is basically option A. And then the third arrow, which is the third possibility of product. The ethoxide can attack at this methyl to break this carbon oxygen bond, and the ethoxide will take out this methyl to give you an ether as a side product. And in that case, the oxonium chain, whatever we were getting in the first step, will stay as it is. Just the methyl of methoxy is being taken out by ethoxide. And in that case, you are going to get option D, isn't it? So we saw that these three possible attacking sites are leading to the formation of A, C, and D. But we did not get option B as any of the possible products. So you have to choose option B as the correct option, which is not going to be formed in this reaction. And this is the description that methoxy participation gives a 5-membered cyclic intermediate on departure of the tosylate. So this is the 5-membered reactive intermediate which will be opened up by the incoming ethoxide. So after that, let us move to the next question. Which is the main product of the following reaction of an amide? So this reaction we have already discussed. So you can try the mechanism by yourself, and you must already know that this is the reaction condition given for Hoffman rearrangement. And in case of Hoffman rearrangement, we observe the formation of a product which is basically amine with one carbon less than the substrate. So you can try out the mechanism of the reaction and you will see that this mechanism is going to give you option C as the final product. Okay, so just practice the mechanism and you will see option C will be formed following this mechanism of Hoffman rearrangement. Then again, for the next question, the reaction conditions of the Curtius rearrangement is given. We have this acyl azide, and what will happen if it is heated first and then it is reacted with water molecule? So the mechanism of Curtius rearrangement have also been discussed already. Like we saw that acyl azide can undergo elimination of nitrogen, and the firstly formed nitrene intermediate immediately gets converted into isocyanate intermediate. And since in the reaction condition you are given water, keep in mind that this isocyanate will react with water molecule here. And by following the same mechanism which has already been discussed, you can choose that this amine will be formed in the given reaction. Okay, option B will be correct answer, but you can practice out the mechanism which we have already discussed in today's session. So with this we have arrived at the last question of today's tutorial. Let us quickly go through the questions. What type of rearrangement reactions we discussed today? At first, we discussed this hydrochlorination of alkene, and we saw that three of the options were possible to form, but the primary carbocation did not form in the reaction, so we chose option D as the correct option. And then we started our discussion for rearrangement reaction, and we discussed the mechanism of the very interesting pinacol-pinacolone rearrangement. Okay, and we saw that dioxonium never forms in rearrangement reactions. So we chose option B as the correct answer. Then we again saw this second pinacol-pinacolone rearrangement, and by going through the reaction mechanism step by step, we saw that option D formed as the major product in this reaction. Okay, and we first of all we formed the most stable carbocation in this reaction. But when we had good leaving group present in the substrate, which does not require very complex reaction condition, we first preferred knocking out that good leaving group. Okay, and in that case we got a secondary carbocation rather than the tertiary carbocation. So this particular reaction followed the semi-pinacol rearrangement reaction pathway, and we got option C as the final product. In the next question, we discussed diazotization of amine, and we saw how the ring expansion happened with the formation of this keto group. Then in the next question, we saw the mechanism of Hofmann rearrangement, and we saw that amine formed from amide by reduction of one carbon number. Again, we discussed these four reactions and we saw that option C, which was supposed to be involving Baeyer-Villiger oxidation reaction condition, it was not giving us the main expected product because the wrong migratory aptitude group was being shifted. So we chose option C as the correct answer. Then we discussed the mechanism of Beckmann rearrangement, and anti-alkyl group to the oxime hydroxyl group was shifting to give us ring expansion again, and we chose option A as the correct answer. And another example of pinacol-pinacolone was discussed where one four-member ring was getting expanded and option A was chose to be correct answer. Then we discussed this particular question where the product was same for both the reactions, but two different carbocations were getting involved in this reaction, and we saw that both 1 and 2 were giving product A by following different mechanisms. Then in the next question we saw that OTS leaving group was knocked out by neighboring group participation of methoxyoxygen, and we got a formation of five-membered cyclic intermediate, and that intermediate could be opened up or attacked by three possible ways to give you A, C and D products, and we saw that B was not forming at any cost. Then I asked you to practice the mechanism of this particular Hoffman rearrangement reaction, and also I have asked you to practice the mechanism of this Curtius rearrangement reaction. So with this we have arrived at the end of this tutorial, and also we have arrived at the end of this particular course, Introductory Organic Chemistry 2. So
Thank
Thank
you.
you very much, madam. In spite of throat infection, your deliberation is very fine, madam. Thank you, madam.
thank you so much for noticing.
You
Actually,
had a
I
very difficulty, even then you presented in a nice manner. Thank you for your effort, madam, on staying. Okay.
thank you so much for noticing my sickness. Yes, I have been having throat infection, and actually, I was having a little difficulty even at the beginning of this course and also at the end of this course. But I hope you enjoyed the lectures and study well. And if you understand the mechanisms, you will find organic chemistry very, very interesting.
As a teacher, I can understand this pain, madam. Okay, thank you. Thank you.
Thank you.
Okay,
Thank
thank
you.
you. Thank you.
Also, madam, your selection of
Yes.
questions are also very interesting.
Thank you so much. Thank you so much.
Selection of
Okay. And feel free to ask any suggestions or questions. And you may get my email IDs or contact details from the NPTEL site. And I would ask you to feel free to ask for any help regarding these organic chemistry course, and study well. All the best for your future endeavor.
Thank you, ma'am.
Thank you.
thank you.
Thank you, ma'am.